Good morning, all of you. I welcome all of you to the class. Today's class is about the bending of unsymmetric beams. And today's class is very, very important because in today's class, we'll be taking our concepts ahead of the bending of symmetric beams. Till now, we have been discussing the beams which are symmetric about some axes. But today, we'll be talking more general cases of the beams which are known as the unsymmetrical beams. Till now, we have been discussing the beams which are mainly symmetric. For example, we have discussed the beam having the rectangular cross section. Okay, this is a symmetrical beam about its centroidal axis. Okay, we have been talking about the beams which are having the circular cross section areas. This is also a symmetrical beam, and we have discussed their bending. In mechanics of material previous classes, we have talked about their normal stresses and shear stresses. Now let's talk about the bending, that is the stress distribution in case of the unsymmetrical beams. As far as the unsymmetrical beams are concerned, as is here, we are having a cross section of a beam. This is a beam that is under observation. Okay, this beam is under observation. We want to study this beam. We want to study the stress distribution in the beam. We want to study its stress distribution as well as the strain distribution. Okay, that is the deformation of this beam is to be understood. But if we look at the cross section of the beam, the cross section of the beam happens to be unsymmetrical. That is given over here. Fine. Now, how do we study such types of beams? In the previous cases, where we had what are known as the pure bending cases, the cases of pure bend. In case of pure bending of beams, we had that the bending moment across the entire span of the beam was constant. The bending moment and across the entire span was constant. We will also assume right now that our beam is under pure bending, that is the bending moment across the entire span of the beam is constant, but the cross section of the beam is not symmetric, it is unsymmetrical. Now, if you look at the bending moment over here, in case of symmetrical beams, we were showing the symmetrical beams in the form of a line, okay, and then we were dictating their moments, their supports. We were saying, let's suppose we are having a pin support over here, and at this very end, let's suppose we are having what is known as a roller support. We had a roller support over here. Fine, and let's suppose this is end A, this is end B, and the total span of the beam is, say, for example, L. Then we were assuming that at any section of the beam, the bending moment is M, which is constant. The moment here is also M, the moment here is also M. The value of the M is constant across the entire span of the beam. That is, our beam is under what is known as the pure bending. This is a pure bending case of the beam. Okay. Now, if you curl your fingers in this direction, in the direction of the arrow, and you assume this to be your x-axis, this is your y-axis, and this is your z-axis. In this case, if you curl your fingers, then your thumb will be along the z-axis. Okay, that is, this moment that is being applied on the beam is along z-axis. We say this is moment along the z-axis. Fine, but when we have an unsymmetrical beam, in case of unsymmetrical beam, the bending moment does not lie exactly along the z-axis. It's not parallel to the z-axis. The moment is not parallel to the z-axis, but it is moment is not exactly along the z-axis. That is, it does not subtend an angle of 90 degrees with respect to x-axis, but this moment subtends some angle. Let's suppose that angle is angle alpha with respect to the x-axis. There is a quite good justification for this. Why we assume that the moment is along at an angle with respect to the x-axis and is not parallel to the z-axis. Okay, there is a reason for it, because the first and foremost reason is that our area happens to be unsymmetrical area. This is totally an unsymmetrical area. Okay, so the moment distribution about this area will not be along z-axis perfectly. It will be at some angle, and that is quite a good justification to assume to start with that the moment does not exactly lie along z-axis, but it subtends some angle with respect to some x-axis, as we will see in the coming part of this lecture. So the moment that is acting on the beam is at some angle with respect to the x-axis and is not exactly parallel to the z-axis, and our cross section happens to be an unsymmetrical cross section. We assume that let the z-axis be the neutral axis of this beam. This is our assumption. Let the z-axis be the neutral axis of this beam, be the neutral axis of this beam, and let's assume that this z-axis happens to pass through point C. We don't know what is C. We don't know what is C. C is quite unknown to us. We are only assuming that z-axis, the z-axis is the neutral axis of our beam, okay? And this is our y-axis, and such that the z and y-axis intersect at point C, which we don't know what this point C means, okay? We are just assuming this is a point C, fine? We are only assuming that z-axis is our neutral axis. Now, after assuming z-axis to be our neutral axis, let's locate a small area element, that is dA. dA is a very small area element on this area, such that this small area is at a distance y from neutral axis z, which we are assuming, and it is at a distance z from the y-axis. Are you getting me? So this small area element is having coordinates y comma z. Fine. We know stress sigma, because of the moment, stress along x-axis is equal minus my divided by I, where y is the distance from the neutral axis. We have also learned that sigma x is also equal, in terms of Young's modulus of elasticity, it's equal minus E curvature at that point, kappa y multiplied by y, okay? So at this point, which is at a distance y from the neutral axis, stress from the previous formula is equal minus E times kappa into y, fine? Now, how much will be the force on this small area element? That will be small force along x-axis will be equal sigma x multiplied by dA. That is equal minus E kappa y into dA. Therefore, the total force along x-axis will be integral of df of x. Okay, that's equal total force along x-axis. That is equal integral of minus E kappa y dA equal to 0. But as far as E into kappa y, they are constant. So it is minus E kappa y will come out. Integral y dA is equal to 0. E cannot be 0. Kappa y cannot be 0. Therefore, integral y dA has to be equal to 0. If this integral y dA is equal to 0, then we essentially know that point C stands for the centroid. C is the centroid. This point C stands for the centroid. Okay, so it means as far as this point C is concerned, from which we are taking to be the origin of our YZ system, is the centroid. This is one thing. Now this essentially happens because we are having the moment. Okay, we are having this moment M. Fine. But if you look at this moment, the basic formula for calculating stress along x-axis is equal minus M y divided by I, where M was the bending moment. This is a fluxural formula we have already derived in the previous lectures. But if you look at, in case of unsymmetrical beams, this M is not perfectly along z-axis, it is subtending some angle. Fine. So it means if you are calculating the stress with the corresponding to some value of M, we have to resolve this M into two components. This M will be having some component along z-axis, which we call as mz, and this will also be having some component along y-axis. It will be like this. Some component along y-axis. It will not be having a component along x-axis. Okay, some component along y-axis, that is my. So we have to see the effect of both the moment my and moment mz in creating the stresses sigma x along x-axis. Okay, along x-axis. Fine. Actually, if you look at this beam bending, unsymmetrical beams, it bends along. It's quite important to visualize. The beam bends along xy plane. Unsymmetrical beam bends along xy plane, as well as along, we should say, along yz plane. Along yz plane. The bending is combination of two. It bends like this, as well as it bends like this. Okay, unsymmetrical beam is having two components of bend. Its bend is along yz plane. Its bend is also along xy. It is a combination of two bends. Okay, two bending moments. as is quite evident from this M, which is not perfectly along z-axis, but it subtends some angle. It has a component along z-axis and component along y-axis, not having a component along x-axis. Now, after locating this point C to be our centroid, okay, now let's assume that the beam is bent in such a way, in such a manner that y-axis is the neutral axis now. So this is our unsymmetrical area of cross section. This was our point C, fine. This was our z-axis, and this is our y-axis. Okay, this is our y-axis. We are taking a very small area element out here, which is, we are taking a small area element dA out here, such that this distance is y and this distance is z. Okay, since the beam bends along YZ plane as well as along XY plane. Okay, so now let's suppose that the beam is bending such that Y is now our neutral axis. Y axis happens to be the neutral axis. Okay, and the bending is along the XZ plane now. That's quite very important to evident. Okay, the XZ plane happens now to be the plane of bending. Therefore, what will be the stress along x-axis? Stress along x-axis will be equal to E minus E times kappa Z, because when you had when we were calculating the bending from the neutral axis, Z was the neutral axis, we were calculating the curvature, the distance from the y-axis. Okay, that was k kappa y. Now y is the neutral axis, so we have to calculate the curvature from y-axis, so it will be k kappa z. Okay, and its distance is z. Okay, therefore small, this is the stress along x-axis, therefore small force along x-axis will be equal sigma x dA, that's equal minus integral E kappa z z dA. Since there is no force acting along x-axis, that has to be equal to 0. Therefore, we get integral z dA is equal to 0. When integral z dA is equal to 0, then that means this point C is the centroid. And like the previous case, Z was the centroidal axis also. This was the centroidal axis. Then y-axis is also the centroidal axis. This is very important. So from the analysis, we obtained that the origin of YZ axis for an unsymmetrical beam must be placed at centroid C. This is quite important, important result that we obtained when we did this much of the analysis. That is, for in case of the unsymmetrical beams, the unsymmetrical beams are bending in such a way that their axis XYZ system has to be placed at the centroid. Okay, now after locating this, so we have to, when we have to do the analysis for unsymmetric beams, first of all we have to find the centroid. Okay, after locating the centroid, that will give us some important information for calculating the stresses and the strains. We have to calculate the bending moments as well. This is very, very important thing, because this is what I was talking initially in my slide number 1. The moment that acts on the beam when the beam is unsymmetric can be resolved into two components. It has a component mz, it has a component my. Okay, analyzing or understanding these moment components along z-axis and y-axis is important. Let's go back to our diagram. The picture that was showing us the bending of unsymmetrical beams. This was the beam in front of us. Okay, unsymmetrical beam subject to bending moment. I am repeatedly saying that it will have a moment component along z-axis. What will this moment component along z-axis do? If you put your thumb in the direction of this moment component along z-axis, then because of this moment component along z-axis, this beam will essentially bend along xy plane like this. Okay, this will be its bending because of this mz. Okay, and this beam does not only bend along xy plane, it also has another plane of bending. Okay, that's yz plane. How? One more component of this m is along y-axis, m y. Now if you put your finger in the direction of this thumb, Okay, then essentially it will bend, but its bend will be now on the xz plane. I'm sorry, I was repeatedly saying yz plane. It is xz plane. It's xz plane. So you have two bends. One bending occurs like this, and another bending occurs like this. Okay, so this is very important to understand. This component, I'm repeating, this component of moment mz, this component of mz, put your thumb in the direction of the mz, then your beam will essentially bend in xy plane. Okay, that will be caused by this mz component. There is one more component, that is the moment component along y-axis my. Put your thumb in the direction, then your beam will essentially bend like this. Okay, so we are having two bends in the beam that we practically observe when the beam is unsymmetric. For unsymmetrical beam, we are having moment mz, we are having moment my. Okay, moment mz and moment my are both responsible for creating forces along x-axis, which is essentially equal to 0. Now let's return back to our slide. This slide, the moment, the bending moment my and mz, the bending moments my and mz, which acts along y and z axis, is shown as, this is moment along y axis, this is moment along z axis. Now we essentially had a small area element. We had a small area element dA. This was the origin of our coordinate system. This is our z axis. This is our y axis. We were saying that this distance is y and this distance for us was equal to z. Now let's first of all see how much is the force on the small area element because of mz. Okay, because of mz, because of moment along z axis, force, as we just saw, small force dfx is equal stress sigma x dA. Okay, on this, at this small area, because of mz, because of mz, because of moment acting along z axis, the force on this small area element will be stress, that is sigma x multiplied by small area dA. So this is the force. Now how much will be the moment? Force multiplied by force arm, that is multiplied by y. Okay, this is the moment. We'll write this as small moment dm on small area element dA because of mz. Now this entire moment, the summation of all the moment, this entire moment that is created over on this small element should be equal to the moment along z axis. This is the moment. This is the moment because at small area element dA along z axis. Okay, so the total moment along z axis will be mz. That will be equal to integral y sigma x dA. Okay, actually your beam happens to be like this. It's supported over here, it is supported over here. Fine. So if you take a section over here, then at this section you will be having two components of the moment. You will be having moment along z axis and moment along y-axis. But the moment that will be created at this point will be in a direction opposite to the moment mz, because the moment that we are calculated inside the material will be the reaction moment in response to the mz. That's why it is shown by sign minus. Okay, so the magnitude will be force multiplied by the force arm and minus. So that's equal minus integral of, in place of sigma x, we'll write sigma x is equal to E kappa y into y, and we have our yda. That is equal, so E and kappa y, by the way, this sigma x is equal to minus will become plus, integral kappa y will come out of integration, so we'll be having y square dA. If you look at this y square dA, it is a second moment of inertia along z axis, so we'll write this as cap E kappa y iz, as is given over here, E into kappa y iz. This is the moment along z axis. Now, so this is the moment along z-axis. Now, what are the, so when we are calculating this mz is the external moment acting along z-axis, and this is the internal moment created inside the material. Now, in the same way, because our moment is having two components, mz and my, what will be my equal? The moment along y-axis will first of all be equal force along x-axis multiplied by z-axis, because our area element dA is over here. This is our small area element. This is z-axis. This is y-axis. If we have to calculate the moment along y-axis, we have to multiply at the distance from the y-axis, that is z. So that will be equal integral sigma x z dA. Sigma x dA is force, z is force arm. That's equal to minus integral sigma x is equal to minus E kappa y minus E kappa y into z into dA. That is equal to minus E kappa y integral y into z dA. If you look at this yz dA, this is known as product of inertia. So this is equal moment along y-axis is equal minus Young's modulus kappa y into product of inertia along the xy system. This is very important. If you look at mz divided by my, that comes out equal iz minus iz divided by iy. So the moments along z and y axis are in the ratio of the second moment of are in the ratio of xyz. Moment of inertia about the z axis divided by the product of inertia about the xy system. So understanding these two important formulas is very important. Understanding these two is very important. That is, we should know what is this mz and how we calculate this my. Okay, so essentially when we talk about my and mz, the moment acting along the y-axis, the moment acting along the z-axis, their understanding is overall important if we have to calculate the moments along z and moments along y-axis. So the external moment that to which the unsymmetric beam was subjected was m. Now this beam moment has been resolved into two components, that is mz and my, such that this is the expression for mz and this is the expression for my. Let's move ahead, and after finding this mz and my, we go to the conclusions. The conclusions are, if the z-axis is selected in an arbitrary direction through the centroid, it will be the neutral axis only if the moments my and mz act about y and z axis, and only if these moments are in the ratio established by the equations previously. This is very important. That is, we are saying we had just assumed that this z-axis, we have just assumed that this z-axis is our neutral axis. We can assume let this to be our neutral axis passing through the centroid, then this will be our y-axis. Okay, if you look at your moment along z-axis and moment along y-axis, kappa y is constant, E is constant. It is simply the function of iz and ixy. But we know from Mohr's circle constructions that iz is a function of theta and iyz is also a function of theta. So if you change the angle of this z-axis, the angle of y-axis will also change. Then we will say this z-axis will always be our neutral axis, provided this z-axis passes through the centroid. Okay, as long as this z-axis is passing through the centroid, it represents our neutral axis, provided the moment along z-axis and the moment along y-axis always remain in this ratio. That is, if your mz by my is always equal to minus iz divided by ixy. As long as this ratio is maintained in case of unsymmetric beams, we will say any z y axis happens to be our system of neutral axis. Any zy axis system is a system of neutral axis as long as this ratio is maintained by those x and y systems. This is to be maintained. This is conclusion number one from this unsymmetrical beam analysis. Second conclusion is, if z-axis is selected as a principal axis, then the product of inertia about yz is equal to 0, and the only bending moment is mz. In that case, the z-axis is the neutral axis. Bending takes place in the xy plane, and the moment mzx in that plane. Thus, bending occurs in a manner analogous to that of symmetrical beams. What does this state? Let's suppose we have been saying that somebody will say, let me take this to be my z-axis. This is also passing through the centroid. Therefore, this is also a neutral axis. This will be the y-axis then. Z and y are always perpendicular to each other. I just stated that is only the case. We can say that this new z-axis, let me write this as z prime, y prime. This is also a system of your neutral axis such that the moment along z-axis, that is mz prime, new axis, and the moment along this y prime should always be equal iy divided by ixy. If this ratio is maintained, then your z prime, y prime axis is also a system of your neutral axis. Now, out of all these axes, somebody will say, let me suppose this to be my z axis, then this is my y axis. This is also passing through the centroid. Okay, this is also a system of neutral axis. We will say yes, as long as this ratio is maintained. But out of all these axes, since your moment of inertia about different axes will be different, but we know there will be a particular axis system, there will be a particular z, there will be a particular zy system or yz system where your moment of inertia will be maximum. Okay, you are saying that axis as a principal axis. We know across the principal axis, the product of inertia ixy is always equal to 0. Since you are having zy system, you will say iyz about principal axis is equal to 0. Therefore, this term will be equal to 0. Therefore, the only moment that you will be having will be this moment, mz. That is, your beam will have only one bending moment equation or only one moment, that is mz. The beam behaves essentially in the same way as a symmetrical beam. The bending in this case is equivalent to a symmetrical beam bending. Okay, so that is a case when one of the axes happens to be